Okay, so the two-dimensional heat equation. So this is the outline of steps that we need to do. So we'll start with, of course, the statement of the problem. And so the two-dimensional heat equation is U sub T equals C squared UXX, or second derivative in X and Y, and a first derivative in T, and C is some constant, which doesn't really matter that much. We need the domain, so this is the PDE itself. That's the equation. We need domains, right? And we're thinking of, X being between 0 and A, Y between 0 and that's not supposed to be a comma, B, and T greater than 0. So boundary conditions. We want on all boundaries that it is 0. So when X is 0 or X is A, the boundary is on X, we want U to be 0. And when Y is 0 or Y is B, which is the boundaries on Y, we want that to be 0. And so that's our boundary conditions. What else do we need is the initial condition. So when T is 0, our solution should be some function f of xy. Okay, so what's the idea here? What's the image that's going on? Well, we have a rectangle in the plane, and we think of this as being a thin sheet of metal. And it goes from 0 to A. That's our X. And it goes from 0 to B. That's our Y. All along the boundaries, we think of U as being the temperature. So it's a heat. Boundaries are all kept at 0 degrees. And inside the square, we have some initial temperature distribution given by our initial condition. And then the question is, what happens to the temperature? Right. And of course, the temperature over time has to smooth out so that everything's at 0 degrees, because we're keeping the boundaries at 0, which means if the plate inside is colder than 0, we're going to pump heat in. And if the plate inside is hotter than 0, we're going to drag heat out. So everything will come down to 0 eventually. Okay, so second thing to do once we've stated the problem is do the separation of variables and find the ODEs and see what the boundary conditions are. So we assume, let me put my cursor down here. We assume that our function, our temperature distribution is given in space by X and Y and in time by T, and we're going to assume that that's a function of X and times a function of Y times a function of T. So capital X of little x, this means I have some function capital X that depends only on little x, some function capital Y that depends only on little y, some function capital T that depends only on T. So plug into the PDE, and what do we get? Well, we get, I'm going to suppress the small letters. The PDE is the derivative with respect to time. So if we differentiate all this with, if we differentiate U with respect to time, the only thing that gets differentiated is the T of T part. And that would be C squared. Differentiating with respect to X twice just means differentiating the X part. So we get X sub X Y T plus X Y sub Y Y T. Great. And then we'll divide by x, y, t. Right? Divide by the product, and that gives us t of t over t, because on this term, the x, y cancels out, equals c squared x of xx over x plus y sub y over y. Oop, yep, and the t's go away. And so there's our separation of variables. And what we've done now is the left-hand side depends only on t. There we go. It's a time term only. Right-hand side RHS depends only on x and y. So the left-hand side is a function of time, the right-hand side is a function of space. The only way that a function of time can be equal to a function of space is if they're both equal to a constant. So we have t sub t over t equals k1 c squared x sub x over x plus y sub y over y. And in fact, I want the c squared to be over with the t. So we will write that as t sub t over c squared t equals k1. And x sub x over x plus y sub y over y equals k1. And k1 is our first separation constant. And so that gets me an ODE for time. And that's dt minus k1 c squared t equals 0. Put that in a little box. Right, you just take this equation, multiply both sides by c squared t, and yeah, and then move it all to the same side. So it gives us a time function. And I forgot the domain. This is all for t greater than 0 is the solution that we're searching for. So the other differential equation we have is this, and we can actually separate that. We'll just move the y terms over to the right. So that gives me x over x equals k1 minus y over y. And now the left-hand side depends only on x. Right-hand side depends only on y, little x and little y. So the only way you can have a function that depends only on x equal to a function that depends only on y is if they're both equal to the same constant. So x over x equals k2, that's our second separation constant, equals k1 y over y. So we get ODE for x is x, d squared x dx squared, since we're only dealing with one variable here, minus k2x equals 0, with the boundary conditions, x of 0 equals 0, x of a equals 0, and I'm at the bottom of this page. So we have this, and we also have our domain, that x is between 0 and a. Okay. So there's our ordinary differential equation for x. So we are almost to being able to state all of them. The ODE for y. So we'll take the right-hand side of this, we can rewrite that as d squared y dy squared. Move that over, we get k2 minus k1, y equals 0, with the boundary conditions that y of 0 equals 0, y of b equals 0, and little y, our variable, is between 0 and b. So that should be k1 minus k2. I might have gotten a sign wrong. So move this over. No, k2 minus k1, let's move it. Okay, so there's our OD for y and our OD for x. So we've set up our ordinary differential equations that arise from our separation of variables. And so now I'll bring this back up, and the job is to solve the ODEs. Along the way, the separation constants K1 and K2 will be quantized, right? What that means is that we'll be able to nail down some statements for that. So we'll solve, oops, let's put the cursor down here again. Oh, I keep putting the cursor back up. Solve the ODE for x, and this is d squared x dx squared minus k2x equals 0. So 3 cases. Case 1 is k2 is positive. And let me remember my boundary conditions. X at 0 equals 0. X at a equals 0. So the solution to the equation itself of k2 equals 0 is that x equals some constant c1 e to the square root of k2x plus c2 e to the minus square root of k2x. So the boundary conditions tell us that x at 0, this is a capital X, x at 0 from this equation equals c1 plus c2, and that has to be equal to 0 because that's what it's set to, and x at a, which equals c1 e to the square root of k2a plus c2 e to the minus square root of k2a equals 0. But pair of equations, linear equations, and 2 unknowns, right? C1 and C2 are the unknowns. The only solution is C1 equals 0, C2 equals 0. So K2 being greater than 0 doesn't lead us to anything interesting. What about C2, K2 equal to 0? So K2 equal to 0, that's case 2. And then that just becomes the second derivative equals to 0. So x equals a line, which traditionally is mx plus b. And then we apply the boundary conditions. And note that the boundary conditions are really important in creating particular solutions. Boundary conditions are really important in structuring what the solutions to partial differential equations can be. So x of 0 equals b if you plug in 0 for x, and that has to be 0 by the boundary condition, so b equals 0. So that means x at a has to be equal to m times a plus 0, but we already know that b is equal to 0, and that must be equal to 0, which means m equals 0. So the only solution here is x equals 0. And we should point out that this also implies that x equals 0. So the only interesting case we get is if K2 is negative, and then we'll get some sines and cosines. So case 3, K2 is less than 0, and in which case we'll define K2 to be equal to minus mu squared. And that just helps us with the notation a little bit, right? So if K2 is a negative number, then it's minus some number squared. So our differential equation is d squared x dx squared plus mu squared x equals 0 with boundary conditions x of 0 equals 0, x of a equals 0. So x equals c1 cosine mu x plus c2 sine mu x, right? Because it's the solution to that kind of differential equation. So let's see, boundary conditions. X at 0, or if you plug 0 into the formula for x, you get c1 times cosine of 0, which is 1, plus c2 times sine of 0, which is 0. So x of 0 equals c1, but that equals 0. So what's x of a equal to? We already know that c1 equals 0, so it's just going to be c2 sine mu times a, if we plug in a for x, and that must be equal to 0. But this equation implies that mu a has to be a multiple of pi, and we use n to stand for an integer some multiple of pi. So that tells us, and here's the quantization of our parameter, mu has to be an integer times pi over a. So there's in fact infinitely many possible values for mu, but they're discrete, right? They don't accumulate at any point. So what is x then? Well, we have infinitely many of them, xn equals, and all we have is the sine part. So for each value of n, we get a different x sub n. We get a different possible solution. And let's note here that K1, let's get some light on my notes here so I can see what I'm doing. K1 was set equal to minus mu squared. And so that means that K1 is equal to minus n pi over a squared. And so that's our separation constant, our first separation constant, and it's been quantized. Okay, so equation for y. And the equation for y was d squared y dy squared minus, well, but I need to be a little bit careful here, because this is K2 is actually equal to minus mu squared. So this is not K1. This is K2, the second separation constant, that's equal to minus n pi over a squared. So d squared y dt squared was d squared y dt squared plus K2 minus K1 times y equals 0 with the boundary conditions y at 0 equals 0, y at b equals 0. Okay, so we know that K2 equals minus mu squared, and we'll just call it mu squared for the moment. And that gives me d squared y dt squared minus mu squared plus K1 y equals 0 with these boundary conditions. And we get the same three cases as above. And similar arguments suggest that if mu squared plus K1 is greater than 0 or equal to 0, get only y equals 0 as solution. which is not that interesting. So we want to see what happens for case 3, and I'm not going to go through those in detail, but you can do that for yourself. So case 3 would be mu squared plus k1 less than 0. And in that case, we'll do the same thing as we did before. We'll define nu. This is at least my version of the Greek letter nu, equal to minus nu squared equal to mu squared plus k1. Right, so if this is negative, we turn it into that, and that makes our differential equation d squared y dt squared plus nu squared y equals to 0. Right, and then we get the solution, same process as above, involving the boundary conditions. Nu has to turn out to be something, an integer of the form m pi over b. And y is now, since nu is quantized, sine of nu y. I know my nu's don't look like much of anything. And nu is m pi over b y. Right, so that gives us y sub m of y. And note that if nu is m pi over b, minus nu squared minus mu squared equals k1. That's from this equation. Minus nu squared is m over pi b quantity squared. Mu squared is n pi over a because it came from x squared. And the whole thing has got a minus sign floating out front. And that's our first separation constant, k1. And so now we've quantized both of our constants. The last thing to solve for is time. And time is dt minus k1 c squared t equals 0. So the solution for that is t equals some constant. Let's be a little bit careful here. T sub mn as a function of t equals some constant, we'll call c1 again, exponent of k1 c squared little t. I'm using a sort of an alternative notation, I think probably you've seen, but it's the same notation. These two things mean the same thing. The XP is useful because then that allows us to say, well, I can write out this long, complicated thing. T sub mn of t is c1 e raised to, well, k1 is minus the quantity right up there, m pi over b squared plus n pi over a squared times c squared times t. Great, so now we have all three of our solutions. We'll just note something here. We've quantized everything, and note that as t goes to infinity, capital T goes to 0, right? As time goes on, the temperature in the plate approaches 0, and that's because of this exponential term that's got a negative exponent. Great. So what are the normal modes and what's the series solution? So we've got 3 different equations. And we'll say that UNM is a normal mode. It depends on X and Y and T, and it's a product of the 3 types of solutions we have. So our normal mode, X comma Y comma T, is equal to sine of n pi over a x times sine m pi over b y times the exponent of the exponential of n pi over a squared plus m pi over a squared c squared t. And so that's our normal modes. And so the solution n equals 1 to infinity, sum m equals 1 to infinity of these solutions times the coefficient. So how do we look at this thing? If we think back to sort of what vectors and expansion in terms means, if we think of this as a vector, we think of these things as basis vectors, then we're saying, well, this vector is a bunch of coefficients times basis vectors all added together, right? So U is a linear combination of these basis vectors with these coefficients. And now the question is, how do we get to the coefficients? And this is where we use some orthogonality. And to use orthogonality, what do we need? We need a inner product. So every PDE sort of gets its own inner product. It's an interesting fact that we can construct so many of these. So what's the inner product for this problem? We'll define the inner product of 2 functions, f and g, to be the integral from 0 to a, integral from 0 to b, f of x comma y, g of x comma y, because remember we're in 2 dimensions here, dy dx. So that's the inner product. You can check that that actually meets all the standards for inner product. It's linear, it's symmetric, and the inner product of a function equals 0 only means function with itself equals 0 only means that the function is 0. So that's the inner product. So we want to use the initial condition to evaluate what the coefficients a and m are. And the initial condition is that u at x comma y comma 0 is some function f of x, y that was given to us. Or what that means is that the sum of a n comma m u n m of x comma y comma 0 equals f of x, y. And so if we put t equal to 0 in these functions, that means that this exponential term is going to be 1, and we're just left with sum n equals 1 to infinity, sum m equals 1 to infinity an comma m sine n pi over a x cosine n pi over b, not cosine, sine of n pi over b y equals f of x y. So there's our initial condition. Now I'm going to, for just ease of notation, define phi of m comma n as a function of x comma y. We'll define that to be equal to sine n pi over a x sine m pi over b y. So the double sum n equals 1 to infinity, m equals 1 to infinity, a n comma m v m comma n equals f. That's this written in a slightly more compact manner. And we will note that the phi m comma n are an orthogonal family of vectors under this, of functions under this inner product up ahead, up above. Okay, so what does that mean about that? If the pair mn does not equal the pair m prime n prime, and that means that either m is not equal to m prime or n is not equal to n prime, then the inner product of phi m comma n with phi of m prime comma n prime equals 0. And you can check that. It's an integral. It's not too hard to do. It's tedious, but it's not hard to check. So what are the a and m? What are the coefficients then? So if we want to find a particular, say, aij coefficient, what we'll do is we'll take this equation up here, and we'll just take the inner product of that. N equals 1 to infinity, sum m equals 1 to infinity, a n m phi mn. I really should have my m's and my n's in the same order. With the function phi ij, that particular function, and that will equal, if we're taking the inner product of the left side, that should equal the inner product of the right side with phi ij. Good. So we know the inner product is a linear thing, so this becomes the sum n equals 1 to infinity, sum m equals 1 to infinity, a m n times the inner product of phi m n with phi ij, and that should equal f of the inner product of these two. Great. This is 0 unless m equals I and n equals j. So what do we get on the left-hand side? You just get a I sub j times the inner product of phi I sub j with itself. And that's equal to f of phi ij. So you can solve this for a sub ij, right? This is a number, this is a number. You find this number, you divide it by that other number. Remember that these are all double integrals. So this is actually the double integral of integral from a, 0 to a, 0 to b. Now phi ij is sine ni over a x, sine of nj over b x. And the inner product is itself multiplied with itself, so we'll put a squared on that. dy dx. And that has to be equal to the right-hand side, which is the inner product of f with phi j. And so that should be equal to the double integral 0 to a, 0 to b, f of xy, which is our initial condition, times sine of ni over a x sine mj over b. This is an m here, y, right? And that's also y, dy dx. Right? Evaluate those two integrals, and that will give you the solution. One thing to note, I'm not going to write out the whole integral, but phi ij, the inner product of phi ij with itself is b over 4 equals, right, the area of our metal plate divided by 4. So what is our solution at the end of the road? U of x, y, t equals the sum, double sum, n equals 1 to infinity, m equals 1 to infinity, a sub n comma m, sine of n pi over a x, sine of m pi over b y, times, and I'll continue on the next line because this is a very long time, the time part, which is n pi over a squared plus m pi over b, no, not squared there, squared here, c squared t. So that's our solution with a formula for the coefficients. And that is, given that we know that this is AB over 4, it'll be 4 over AB times the integral from 0 to A, 0 to B, f of x times sine m, I'll get everything backwards, n pi over A x sine m pi over B y dy dx. And there's our solution.